Hi, my name's Helen Reynolds. I'm a teacher trainer and I'm here to share with you some ideas today about inquiry-based learning. I taught for 22 years in a state school in the UK. Teaching about the inquiry-based approach is something that I'm really passionate about, and I'd like to share some ideas with you today about things that you can do with students and reasons for doing that, because for quite a long time we had a traditional approach to what students actually did when they did practical work in science. It was very teacher-led. It was teacher instructions that students followed, and the inquiry-based approach is a different way of looking at a very multifaceted aspect of what it means to do science. So what I'd like to do is talk about some of those different types of activities. So as opposed to activities such as learning about the law of reflection, so you learn about reflection and then you take the equipment and you do that experiment. That would be a very traditional approach to inquiry. This is about more open-ended investigations where students can find things out for themselves, but also learn about the way that science works. One of the first things that scientists actually do, and it's something we tend to miss, is they actually ask questions. So they find out about the universe by making observations. It seems like a really obvious thing. It's not something we talk a lot about to students, and I think it's really important to do that. And it's something that they can get into themselves. They can get into the idea that they can collect data and then they can ask questions. So, for example, they would study something like variation when they are quite early on in their science, secondary science career certainly. So they might talk about why things are different from each other, and they might talk about genes perhaps and the environment, the interplay of those things. They might go out and measure things. They might measure plants. But actually, if you're in a classroom, you've got organisms in front of you. You have students, and they are organisms and they vary. And so you can actually get data from them, and then they can start to look at that data and ask questions. So one of the things you can ask them is about measuring the size of their hand. So I have my hand, and I think about the size of my hand, and I can measure it in a variety of ways. And so we have a group of students, and they're all measuring their hands. Let's say we're going to take the distance from here to here. So their hand span length, and then they take that number, they go write that number on the board. So they have done a data collection exercise, and we have this data now on the board. And that's the first step. We're collecting data. But it's very important when you've collected data to present that data as well. So when you do this with students, it's really interesting because you can say, okay, we have these numbers now, how can we present this data? And if you leave them to think about it and talk about it in groups, then they'll come up with ideas that perhaps we want to know about. We would call it a distribution. They don't have that language, but they've got an idea that it would be interesting to know the kind of ranges, the biggest, the smallest, the numbers that have this different size. So it's a simple exercise on the one hand, and they can collect the data and then they can communicate that data. And that's part of scientific inquiry. That's part of what scientists do. So there we have our distribution. We have our hands and we know what those hands look like. So perhaps there's a different part of us that has a different kind of distribution. Let's try that out. So we could measure the size of our arm. We could decide about the distance from our elbow to the tip of our fingers, perhaps. That could be our arm length. We could do the same thing. We can produce the same set of data on the board, and we can look at displaying that data. And now, this is the really important thing. Now we can start to ask questions about links between things. So we've got our hand size, we've got our arm size. Is there a link between those things? How can we work that out? How can we collect that kind of data? Now we need to collect the data that's linked. And that's a really key thing for students to see, because it's not just about this distance or this distance, it's about how those two things are linked together. So if you then ask the students to go and do that, they'll produce a table that's got 3 columns. I may hear you thinking, why is there 3? There are 3 because for a student, what's also important, as well as the size of the hand and the arm, is the name of the person. So the name of the person is important as well. So they will have the name, the hand size and the arm size. And then you ask them how they're going to display that. And now it's confusing because we've got the name. What are we going to do with the name? And by talking about what it is that's important and what we're trying to get at, they begin to realise that actually it's not the name that's important. It's the hand size and it's the arm size. It's the link between those two numbers. And when we plot a graph in science, that's what we're doing. We're actually trying to find the link between these two variables. We then start to talk about variables. So that's an exercise that I've done with students in classrooms, and it's great fun, and they begin to realise that the graphing aspect isn't just a mechanism that the teacher tells you to do. there's a reason for it, and the reason is to find the link between two apparently different things. So that's one exercise, but the idea behind it is twofold. You have data, and the data generates a question. Is there a link between these two things? Then, once you've got your question, you can collect further data in order to answer it. So I like to start with something like that fairly early on, and then they can get the idea that data is really, really important for two different reasons. So data is really, really important in science, and one of the things that you can use the data for is to answer questions. And I think it's really good to talk to students about the kind of questions that science answers, because actually, if we're not careful, they come out of their science education thinking that science will have the answer to absolutely everything, which it won't. And this is something that is fine. It's okay to go out into the world knowing that there are questions that science can't answer. And so getting them to ask questions is really important, and they might be quite big questions, and they might actually end up being questions that science can't answer, but that's fine. So in early on, they might be studying something to do with energy in food. They might be learning about their diet. They might be learning about energy in fuels, and they might be heating up water, and they might be asking questions, for example, about which type of food stores the most energy. So you can have a question such as this, and they can heat up little test tubes full of water with their little bits of peanut or bread and find out about which type of food stores the most energy. That's one type of question. That's a really obvious question for questions that can be answered using data collection. So at the point where they're learning about energy, or it could be at the end of it, it often works better at the end of a topic. They can then start to generate questions on a wide range of topics to do with, subjects to do with energy. And these could be really interesting ones, like what kind of food do chimpanzees eat? Do chimpanzees have the same diet as gorillas, for example? These are questions that science can answer because we can get data from that. We can observe chimpanzees. We can't necessarily put them in a laboratory and do experiments like we do when we heat up the water, but we're still collecting data, so we're still answering scientific questions. We can also ask questions about, should we use fossil fuels in order to heat our homes? These are trickier questions. These are not necessarily questions that science can answer. Questions where people may collect data, and we could collect data about using fossil fuels to heat our own homes. And when we do that, we still end up with perhaps a range of views, because it may not be obvious whether or not we should do something. So there are a whole range of questions, some of which can be answered scientifically, usually collecting data. Not always, sometimes using models, but there are things that we can do that will produce an explanation. And that's really important to understand. There is a set of questions for which science has the answer because we can collect data. But there are equally questions that we can't, and questions where there's a matter of opinion are sometimes questions where science won't necessarily have the answer. Later, there'll be questions where they really don't have the answer, not because there's necessarily an opinion about it, but because it's almost impossible to get data. For example, what happened before the Big Bang? This is something that science really can't answer at the moment. We can't collect data for that, so we can do nothing to answer that question. So it's nice to produce those questions. We can make a wall display of those. We can study the subjects, and then we can discuss the extent to which we actually have answered those questions, and then perhaps make a category of question where we can't actually produce an answer because there is no data to be collected, or we won't agree about it. So asking questions and collecting data is one aspect of scientific inquiry and one aspect of doing science. But there's a whole level that it's quite interesting to talk to students about, which is, how do we know what we know? What are the warrants for actually the knowledge in the textbooks that actually they're learning about? And this, I think, is really, really important for students, not just the students that are going to go on and be scientists, but the students who are not going to be scientists, who are going to pick up the newspaper, they're going to look at things, and scientists will say this and scientists will have explained this. They need to know how it is, what is the process by which it's okay for scientists to say, yes, that is what we know about the world, that's what we understand about the world. And so what we can do is actually try to model, to a small extent, the way in which scientists work and how it is that they do go through the process of collecting data, coming up with explanations, coming up with ideas and publishing those ideas so that everybody else can read all about them. So when I've done this with students, I think it's really important to have something that's quite open-ended, because a lot of the practical work that we do tend to do, especially things that come under the category of investigations, are really often not quite as open-ended as we'd like, because the students, if they thought about it, would probably understand the answer. So we need something open-ended. So one of the things I found works best is making paper planes or gliders. It's simple, it's cheap, and it's quite entertaining, and the students are very motivated to do it. One of the gliders I found works best is an O-wing. So an O-wing is a very straightforward thing. We have little pieces of card like so, and we can make them into O shapes like this, which we can then attach to our straw. Okay, so here is one that I've already made, and if you throw this very gently, then it will glide. And the beauty of it is that you can measure obviously how far it glides, but we can also make measurements of our O-wing, and it's not immediately obvious when you look at it what the dimensions of this O-wing need to be in order for it to fly the furthest. Is it important that this thing is smaller than this? Is the length important? Is the width important? You've got a huge number of different ways that you can investigate this particular thing, and it flies beautifully, so it will produce results. So setting this up with a class means that you give them their O-wing and they can play with it, they can look at it, and then they can decide how they're going to investigate it, and you'll come up with a whole range of different ways of doing an investigation into the way that the O-wing actually glides through the air. But that's not the point. The point is that it's not just about them working collaboratively in groups, which is a very important part of science and something that we can discuss with them, but it's also the fact that they are going to produce a method by which they're going to collect data about their O-wing, and that what they can then do is they can swap that method with other groups who can then try to reproduce their results. So there are two specific areas of doing science with this particular investigation that we're trying to draw attention to with the students. The first is that if they're going to do the experiment in the first place, they'll need to repeat their results. It's not very obvious how far this thing moves through the air and where it lands, so they'll need to repeat them. So there has to be repeatability in the results. And in order for them to produce data that they can rely on, they need to do that. They need to be able to identify outliers, anomalous results, things that don't fit. And so this is quite a good experiment for showing them that that's a really important part of science. But by the end of it, they'll produce two things: a set of data and possibly conclusions based on that data, but they also produce a method. So then they swap that method with another group. Not the results, just the method. And the other group tries to reproduce the data that the first group has got. And that's a really important thing as well, because there is an element of reproducibility in science. Other scientists try to reproduce the results that other scientists have done. And they do that so that we are very sure that the work that the scientists have done is correct. And so what you'll find if you do this with a group of students is that the methods usually are so poor in terms of the detail, it's actually very difficult for the second group to produce the data of the first. So in a sense, that's helpful because they can get back together and discuss the extent to which the methods don't work and make them more detailed. And so once that has happened, they can then come back and compare their results. The results may or may not tally, but that's another discussion that they can have. So there are two aspects of doing the experiment: the repeatability aspect, the groups themselves repeat their results; the reproducibility aspect, you try and repeat somebody else's results; and then finally there is the peer review aspect of it. And this is my personal favourite, is that it comes as quite a surprise to a lot of students that actually there is this level of checking. Some of them think scientists sit in their little rooms with their white coats and all their bubbling liquids, and then suddenly they come up with an idea and then they test it and then they say this is what's happening. They don't realise there is a process, and the process involves submitting your work and having it checked by other people and having other scientists try to get the same results as you before you can go anywhere near actually saying, this is what we found out. So I like to introduce them to the peer review process in this and have them make judgments about the quality of the research that they have been judging. So we have a little competition, and we try to find out which is the best research which we think that particular group can publish based on what they've learned about their gliders. But it's being explicit really about the fact that what they're trying to do is to show how it is in reality science comes to know what it knows. And this is really important because they'll come across lots and lots of different places in their lives where people make claims. People may make claims who aren't scientists, who have no data to support those claims. So they need to be able to challenge, be skeptical, be a little bit skeptical about why it is, how it is that people come to say what they say. So there have been times when I've mentioned to some students that it is not always the case that people are honest about their results, and that sometimes the results that they publish are not honest and true, because people are people, scientists are people, and I think it's important that they know that. There are two classic cases of scientists could not reproduce results, and that was cold fusion, which is probably a little tricky for certainly 11 to 13-year-olds. But there's also all of the data, or the lack of data, around the MMR vaccine and autism, which they may have heard of, and is an interesting case study in results that were just simply not true and that got out into the public domain and caused a lot of panic amongst people. So I think the whole of that exercise illustrates that science has a checking system. It's a very important checking system, and that when they read stuff, by and large, in newspapers, it's going to have come through that process. So they've gone through this process of learning various facets of how science comes to know what it knows. How are you going to find out that they've learned anything from this? So one of the things that I like to do during their time in secondary school was to give them an option of doing a completely free investigation. So as the name suggests, they got to choose what it was that they wanted to investigate. And that in itself was absolutely fascinating, because it is, as you know as a teacher, it's often the questions that they ask you rather than the questions that you ask them that are the most telling about what it is that they know and understand. So I would set them off to go and think up 3 questions that they could investigate. So by now they know that it's got to be data. By now we've got to be able to collect data or make observations. Observations are also data. They would go through a process of negotiation with me about what it was that was going to be a sensible topic to investigate. So this isn't a free investigation in the sense that go off and play with equipment. This was a structured exercise where they had to explain to me what it was that they were trying to find out, why this was a scientific question, their methodology for data collection, things that involve risk assessment, because there were an awful lot of Bunsen burners involved and trying to blow things up. So it had to be safe and it had to be doable. You had to be able to collect data, there had to be a reason, a methodology, and they understood by now that they actually had to produce a method that was reproducible or could be reproducible. So by the end of the process of negotiation, we end up with a huge range of questions. We had one student who wanted to make a detector for cosmic muons, bearing in mind he was 12 at the time, and I take personal responsibility because he said he wanted to investigate space. So we discussed space and the fact that it's probably one of the few observational science, truly observational, solely observational sciences, paleontology and all the other types of science included in that. And if we were going to collect data, although he could stare at the sky, this wasn't particularly helpful. He would need to go and do something else, collect some data, I said. So he went off and investigated things that you could collect from space and realised that muons came from space. Needless to say, it didn't work. But he learnt a lot from doing it, and one of the most important things he explained in his peer review presentations to his group, which I was very proud of, is that science isn't necessarily just about working out what works. Some of the most useful things scientists can do is to find out what doesn't work, because then at least they have closed down an avenue of inquiry that other scientists then don't need to do. So that was kind of entertaining, and he got a great deal out of it and did a lot of research. So The whole structure of that exercise happened over several lessons with, as I say, the negotiation, with the doing of the experiment, some elements of reproducibility. Other students tried to reproduce those results, and then at the end of the exercise, the students would prepare a presentation where they would show their methodology, show their data, show what they'd found out, and there'd be a small element of peer review in terms of judging the quality of that data and the methods that they'd used. And it was hugely motivating for students to actually have that choice and to do those things without being told what to do by the teacher, by me, but having the structure so that it was a useful and valuable exercise, and they understood that they were modelling to a certain extent what it is that scientists do in the real world. So what does research into science education have to say about inquiry-based learning? There's been an awful lot of research, certainly over the last 20-30 years, because people have been very interested in moving away from teacher instruction, teacher-led, into student-led, or at least teacher-guided instruction. And I think it's the middle ground that has been shown to be the most effective here. So in terms of research, John Hattie produced a book, Visible Learning, in 2009. And in that book, it wasn't talking necessarily about science education or inquiry-based learning in science per se. It covered a whole range of different ways, different methodologies, and its effect on the attainment and achievement of students. So he found out that there were significant gains in terms of transferable critical thinking skills, which is certainly something that I saw, and also gains to be made in terms of achievement and in terms of attitude. And attitude is certainly an extremely important thing in science education. In 2012, there was a meta-analysis of 37 specifically research projects into inquiry-based learning in science. And what they did is it was very interesting. They broke that down into 4 particular domains, and they looked at inquiry-based learning in terms of the cognitive domain. That's the stuff in the textbook, the science, the things that students learn. There was also the epistemic domain, the how we know what we know. So what is it? What are the warrants for actually saying that this is the science that we are allowed to put into that textbook? Then there was the social domain. That's to do with communication, the way scientists work together, they collaborate, they don't tend to work in isolation so much anymore, how they talk and communicate with each other, how there is a peer review process, and that's all part of the social domain of science. And then finally there's the procedural domain, which is the section which deals with what we actually do in order to ask questions and decide on methodologies in order to collect data to answer those questions, which has tended to be the sole focus of what kind of practical work we've done in science education. And it's even been a very small subset of the procedural domain, where you're talking about manipulation of equipment, teachers telling you what to do in order to collect numbers, which you then put in tables and plot graphs for no readily apparent reason except you've been told to do so. What works best is when you combine the procedural and the social and the epistemic domains. So you're actually being explicit about the fact that this activity is showing how scientists know what they know, the fact that they need to communicate with each other and collaborate, and that there is a certain methodology around how we actually do science, which is agreed upon by all scientists in terms of asking questions, collecting data and making that data good data in terms of repeatability and reproducibility. So that was really interesting to me. It confirmed what I knew from what I'd done with my students when I read the research, but also what was interesting was that discussing these things with students has a really big impact on the cognitive domain, on what it is that they know about science. So somehow talking about the procedural aspects, the social aspects, and how we know what we know. I think I keep coming back to that. How do scientists know what they know? That makes the science that they know stickier. That makes it easier to understand it. It stays with them, and they can appreciate not only the fact that there is a certain method to science, there is a certain way that scientists go about their work, but that when you learn about that, it makes learning science easier and more enjoyable. What I've learned when I've done this with my students is that it has made a big impact on them in terms of their engagement, not only with learning about how scientists know what they know, but also about learning science. They've enjoyed it and I've enjoyed it, and I hope you've enjoyed watching this and that you take some of these ideas back into the classroom and try them out with your students. Thank you very much.